talk about our recent work on whether transformer large language models can logically reason. And the motivation is that, like, if you go to the social media related to AI today, especially related to large language models, you might find that there's a very interesting debate where on one side, people are taking the fact that large language models can reason as given, and basically doing all kinds of posting like large language models already has achieved PhD level reasoning, or if you can see Sam Altman, he says that AI can do general purpose complex reasoning, and paper titles also say that large language models enables complex reasoning or something. And on the other hand, there are other figures who obviously reject this idea that large language models are or can reason in the first place, and there are researchers that publish a lot of papers saying that current large language models such as GPT-4 or cannot do well planning and doesn't help with chain of thought and can perform self-verification and so on. And basically, they reject the idea that large language models based on machine learning or transformers can reason in the first place and claim that they are just doing statistical modeling of human language, which is, well, you can understand that a lot of their claims are also founded. So why is there such a very large disagreement? So the problem is that there's not a very well-defined way of saying what kind of large language model is formally reasoning, especially in natural language, right? So when we are doing a math problem, even if they are very hard ones, it's very difficult to say that whether it has seen some very similar problems in its training set and just modifying a tiny little bit of its answer, or it's actually doing the reasoning required for this very complicated mathematical problem. And the other problem is that pre-trained large language models are black boxes, and we have no idea what its internal components are doing. So instead, we and other researchers following our line of research think about the problem from the opposite way, where we start with the simplest possible formal reasoning problem that we can think of, and see whether theoretically show whether the underlying architecture of large language models, namely the transformers, can perform these very basic reasoning tasks. What this actually answers a question much more limited in scope, but at least we can have some more clear and justified conclusion. And in particular, we are investigating whether large language models can solve the fundamental logical reasoning three-set problem. Yeah, and just to give a walkthrough about prior works in this line of research, one of the very seminal work in this area is the paper called Transformer Learns Shortcut to Automata, where automata are basically state transition systems where you have a start state, and whenever you get the input, it transitions to another state according to a set of transition rules. And the question is, after some certain input, which state will they end up in? And it's well known that these state transition system, or basically deterministic finite automata, recognizes regular languages. And with this, and what's probably not surprising is that you can just simulate, use every layer of the transformer to simulate one transition at every layer, and as such, for n transitions, or using the notation here, if we have t input tokens or t actions that are performed that results in t transitions of the state transition system, then we can use a transformer of depth t to simulate all of these actions. What this paper shows is that you can actually be more efficient and use only a logarithmic depth. In particular, it basically compresses the finite automata in such a way that it uses this divide and conquer method to basically process two items at a time. And so you only require a logarithmic depth to simulate a run of a finite automata on inputs of length t. What this shows is that, well, transformers is actually quite efficient at doing simulating these basic transition systems. But this still has a little bit of distance towards the reasoning that we typically talk about. And in particular, when we talk about reasoning, we typically talk about transformers generating a lot of tokens. Like when you give a prompt to ChatGPT, it will generate basically a chain of thought of how it approaches this problem before generating the final answer. And a more advanced question is, instead of going through the model in one go, how does the capability of transformers improve if we allow the transformer to have a chain of thought before generating the final answer? And basically, the chain of thought is where you ask a question and the model generates intermediate reasoning steps, which are basically additional tokens before generating the final answer. And formally, it's basically like if we allow intermediate tokens to be generated by the large language model, how does that increase the recognition power of transformers? And in another seminal paper called Attention is Turing Complete, it basically shows that transformers, if you allow it to generate additional tokens, then it can basically simulate a Turing machine one step at a time. Basically, if you see here, this is the image adapted from their paper, and the input is a series of tokens, and at each step, the model takes in this sequence of tokens as long as the states, and outputs the next state, the next state that the Turing machine had, that the Turing machine ends in, the next token that the head of the Turing machine points to, as well as yes, it basically computes only the next state of the Turing machine, as well as the next symbol of the Turing machine. And what it internally does is that it first encodes the transition table of the Turing machine into the weights of the transformer, basically as a lookup table. And given the state and the current input token, it can immediately compute the next state, which direction should the head go. And the next step is that after I know how which position that the Turing machine head ends in, I can look up the last time that this position is ever written to and find out what token was written to this position the last time it was written. So what this basically shows is that given any arbitrary input and given a Turing machine, you can construct a transformer model that can simulate it step by step. And we know that Turing machines can express arbitrary computation. So why is this not the end of this line of research? So the problem is that if you simulate a single tape Turing machine step by step, then it's not a particularly efficient way of reasoning, especially if you consider like, even if you only do integer addition, a single tape Turing machine would only need to go back and forth between these two numbers and write the output multiple times, which makes the number of steps taken by the Turing machine to do a lot of simple problems to be very, very large. But humans obviously does not need to do so many steps when doing basic addition, right? And another issue is that it's not particularly, so the inputs used for this transformer construction is not exactly the same as we typically use in a large language model, where the inputs are tokens, are only tokens. But here, the input for the transformer are the combinations of the current state of the Turing machine as well as the current token, which is it is not clear how to immediately convert this to a Turing machine that accepts only tokens and perform arbitrary computation. And following this, another very recent work, which is very related to our research, shows that you can use large language model to simulate basic arithmetic and solving linear equations in modular arithmetic. So it essentially shows that when given arithmetic like this, it will generate a chain of thought that contains the step-by-step reduction of this input expression. So basically, here it computes 7 plus 5, and it computes 4 times 3, and computes 6 plus 12, and et cetera, and et cetera. So at every step, it reduces the complexity of the formula by performing a single computation and ultimately results in the final answer. And similarly, for linear equations, it generates a chain of thought that basically does Gaussian elimination. So what this means is that this result is impressive, although it's very easy for humans to do as well, but it's impressive in that large language models can do this step-by-step reasoning by only generating the next token, and then we have a theoretical proof that such a transformer exists. And we, inspired by this work, we think about like, well, can we extend this to a fundamental logical reasoning problem? And specifically, we choose 3-set because it is a NP-hard logical reasoning problem that requires multiple runs and trial and error. Okay, so our core theoretical result is that there exists a decoder-only transformer for any for any number of variables and maximum number of clauses. There exists a decoder-only transformer that can decide all 3-set instances within this bound using chain of thought reasoning. And just as a clarification, you may be wondering how this is possible given that 3-set is NP-hard. The point is that the chain of thought taken by our transformer to produce the final answer is worst case exponential in size, so we don't aim to break the P versus NP hypothesis. And as we will show later, our theoretical construction using the chain of thought process to simulate logical deduction and backtracking, and use it to represent the human reasoning process of trial and error, which is quite common in human reasoning, because if we try to solve problems, we typically want to try different directions of solving the problem. And if it doesn't work, we would try another direction while keeping some of the learned lessons we learned when trying the first method. Trying the first method. So basically, the high-level implication is that there are transformer-based large language models that can strictly perform Boolean logical reasoning and perform a trial and error with backtracking process. And compared with simulating Turing machine step by step, our chain of thought reasoning also processes the entire formula, which includes which may be a very, very long logical formula at once, instead of like a single type Turing machine requiring to go back and forth between the formula. And here we have a visual illustration of the chain of thought used by our theoretical construction. So essentially, the input is a three-set formula. So a three-set formula is a logical formula that is organized into ends of clauses where each clause is a or of several literals. And in particular, this logical formula is basically every square here is a clause, and a clause contains several literals ORed together, and they are AND together to form the full three-set formula. And the purpose of the three-set problem is to figure out whether there exists an assignment to all of the variables so that this formula evaluates to true. And the chain of thought basically simulates a trial and error process. So at each step, it either chooses a variable, chooses some variable from the current unassigned variables and try assigning it to either true or false. So basically the first step, it tries setting x2 to true, and then it also tries setting x1 to true, and trying to perform deductions. And deductions are basically trying to find a clause where all of the variables are set to false except for one of them. And because if you want the formula to be satisfied, then every clause need to have at least one literal that is set to true. So if all but one of the literals are set to false, then it means that in order to satisfy the formula, the last literal must be true. So basically, here we can see that we already know that x2 is true and x1 is true. According to this clause, we know that the not x2 literal, so a literal is a variable or its negation. So the not x2 literal here is false, and the not x1 literal here is also false. And this means that the x4 literal must be not x4 literal must be true, and thus the x4 must be set to false. So this is a deduction we can make based on the current assignment and according to the original formula. And essentially, it will repeatedly try to perform deductions based on existing assignment. And when it basically encounters a conflict in that, in this clause, for example, according to the current assignment, x2 is true, x1 is true, and x3 is true, then you can see that this entire clause has all three literals set to false. This means that this forms a conflict, and the final formula has already evaluated to false under the current assignment. And when it encounters a conflict, it will try to find the previous, the last assumption we made. And because this assumption leads to conflict, which is basically false, then we know that the negation of the conflict must be true. And basically, we flip this assumption and try this again. Try the deduction again. So basically, so all of the tokens in typewriter font are generated by the model. So basically, the model would take this as an input and generate the first token assume, and generate the second token 2, generate the third token assume, generate the fourth token 1, and et cetera, and et cetera. And ultimately, it will, after producing a very long chain of thought, it will produce a final set or unset based on the entire reasoning chain. Okay, so is there any questions regarding what this means?
I had a quick one. Can you go back to the theorem, I think 4.5?
Yes.
Yeah, were you able to place a bound on the number of tokens needed for the chain of thought to solve?
Oh, yes. So in the formal version, the bound is, so for p number of variables, the bound is 2p plus 1 times 2 to the p. And you can see this because every attempt,
Mhm.
at the worst case, each variable would correspond to 2 tokens, where each is assumed and followed by the variable, and ultimately and the final one is backtrack. So every line takes at least 2p plus 1, 2p plus 1 tokens, and in the worst case, we will just try all the possible assignments. So there are 2 to the p possible assignments. So the worst case is 2p plus 1 times 2 to the p. But I mean, this is almost never achieved in practice, but it's a little bit difficult to provide theoretical analysis to strictly show that it can do better for all possible formulas.
Gotcha. Thank you.
Yes. Okay. So I will talk a little bit about 3-SAT. So basically, SAT is about, so Boolean formulas are formulas with Boolean variables and logical operators. And in 3-SAT, the Boolean formulas are in conjunctive normal form, where, as you probably already seen in the previous slide, it's and of clauses where each clause is or of several literals, and every literal is either a variable or its negation. And the 3-SAT basically requires that every clause contains at most 3 literals. And the reason that this 3-SAT problem is interesting is that every SAT instance can be converted to a 3-SAT instance with a linear increase in size. So essentially, if we solve 3-SAT, then it requires almost the same level of complexity of solving arbitrary SAT problems. So considering only 3-SAT problems doesn't really reduce the complexity of SAT solving. And so why do we consider SAT solving in the first place? So conceptually, SAT solving represents a basic formal proof system. And in fact, it's one of the most basic possible proof system, which is the resolution system. And a SAT solver essentially internally implements a resolution proof system, but we'll not talk about that. The point is that SAT solving is implicitly proving logical theorems, and that is why we think that it is representative of basic reasoning. And it is also known to be NP hard or NP complete. So it strictly requires multiple rounds of trial and error. And it is also actually implicit in many everyday tasks, such as solving puzzles and scheduling and so on. And in fact, for every puzzle, you can convert it like Sudoku and scheduling. You can actually just convert it into a SAT formula and put it in a SAT solver to solve it. Although it may take a longer time, but it's definitely technically possible. And even though SAT is NP hard, there are actually very efficient SAT solvers that can solve SAT formulas of tens of thousands of variables and hundreds of thousands of clauses. And it is also widely used in formal verification, symbolic execution, and model checking. And as a result of these very efficient SAT solvers, we know very well how to solve SAT. And our core theoretical result is that for every bounded number, for every bound on the variable size and clause number of clauses, there are we can construct a transformer that can decide the satisfiability of a 3-SAT instance using chain of thought. And in particular, there are 2 special tokens, SAT and unsat, so that if the input SAT 3-SAT instance is satisfiable, it will output SAT, and otherwise it will generate tokens before outputting SAT. And if the formula is satisfiable, and it will generate tokens and output unsat if the formula is unsatisfiable. And yeah, the more formal version is here. Okay, Yes. So basically, for every P and C, there exists a transformer model so we model the transformer model as a model that takes in a sequence of tokens in the vocabulary and outputs the next token. And it autoregressively decides 3 set in no more than, well, the bound we just talked about. And it has 7 layers, 5 heads, and with some number of parameters depending on depending quadratically on the number of variables. Is this clear? Okay. Yes, I just talked about this. So now I dive a little bit about how do we even prove that this is this is correct. So the main problem with proving the correctness of a transformer model using chain of thought is that if we want to formally prove its correctness, we need to show that it is equivalent to some either proof system or a SAT-solving program. But these are very different things. So how do we even prove the equivalence between a transformer model using chain of thought versus a proof system or a SAT-solving algorithm, right? So I'll first talk about the algorithm that is used for SAT-solving, which is also the algorithm used in practice with a lot of, although people definitely have done a lot of optimizations. But basically, the DPLL algorithm for SAT-solving is the basis for almost all SAT-solving algorithm used in practice, and it's also what is simulated by our transformer with chain of thought. So it basically combines searching, which is trying different assignments and seeing whether the formula evaluates to true under this assignment, and wait, this is not working. Okay, and deduction, which is trying to deduce new facts from the set of known facts, or in the case of SAT-solving, it is deducing new variable assignments from existing ones based on the formula. And in the DPLL algorithm, search is represented by decision, which is selecting an unassigned variable and assign a value to it, which is represented by the assume operation in our chain of thought. And deduction is represented by unit propagation, which basically tries to find a clause for which all the literals are assigned to false except one, and that literal must be true for the formula to be true. And if you implement the DPLL algorithm procedurally, it will look like a recursive algorithm where you first try to make deductions, and if making deductions make the formula true, you return set. If making deductions make the formula false, you return unset. Otherwise, you pick a variable, assign it true, do recursion, and otherwise, if that results in a conflict, then we try assigning the variable to the opposite direction and try and do recursion of the DPLL algorithm, which definitely works very well in practice. The problem with this formulation is that it is difficult to prove that our chain of thought is equivalent to this program. So instead, how we prove that it is actually a correct SAT solver is that we model SAT solving as abstractly as the transition system, where a transition system is basically a set of states and a set of transitions as well as a start state. And basically, for a set of states, we define a transition relation on it such that from each state, you can transition to one or more of the other states. And if S1 can just transition to X2, we use arrow to denote this relationship. And this is actually a very, very broad definition because first, the set of states can be anything and it can even be infinite. And you can even include the definition of Turing machines as a simple state transition system. If you include the entire type, the current position as well as the current state in the Turing machine as the set of states, and then you can easily construct a transition system that represents the entire Turing machine. And it also includes finite automata and chain of thought reasoning, as we will explain later. And the idea is that we can convert both the chain of thought reasoning of our model, as well as DPLL, which is the SAT-solving algorithm, as transition systems and prove a simulation argument between them. And now the question is, how do we formulate a SAT-solving algorithm as a transition system? So to define the transition system, we need to define the set of states. So this is actually a very nice old paper that did this for us, and we leverage a lot of the theorems proved in their work to prove the correctness of our construction. So this part is basically describing the formulation of the abstract DPL algorithm we use to prove the correctness of our construction. So essentially, the states are the tuple of M and F, and also the special state set and N set, where M is basically an annotated sequence of a partial assignment. And if you recall from our previous example, and when producing the chain of thought, we have a sequence of some of the variables are assumed and some of the variables are a result from deduction. And we put all of them in a sequence, we can say that the first assumption x2 to true is a decision, which is the name for assumption in DPLL. And similarly, the x1 is equal to true is a decision, and x4 is equal to false is a decision. And we use a more condensed notation. We just denote x2d, x1d, not x4, where not x4 means x4 is assigned to false, x2 means x2 is assigned to true, and d means x2, the x2 is equal to true is a decision. So basically, we condense this into a much more compact notation, and F is just the three-set formula, which is a sequence of clauses. And if F evaluates true under M, we use this symbol here called the model symbol to say that M models F. And similarly, if a clause evaluates true under F, we also say that M models the clause. And the transitions, oh yes. So you can already see that this is very similar to the chain of thought we used for our theoretical construction. So basically this part is the model input is the formula, the F part. And to get the M part, you basically just find the previous backtrack operation to find the current line that we are on, basically. And suppose that you're at this point, then you just convert this part and use the condensed notation. So basically this will be x2d, not x1, not x4. And the state transition is that there are several state transitions, and so we start with the simpler ones. So basically, the first way is when do we decide that a formula is unsatisfiable, and the corresponding state transition is that if there's a clause that contradicts M, which is represented by M models not C, then we see, and M also does not contain decision literals, or in a more casual term, M contains no assumptions, then we know that every assignment must make the formula evaluate to false. And such we know that the formula is unsatisfiable. And similarly, if the M already satisfies the formula, then it is definitely satisfiable since M is a satisfying assignment. And so to make an assumption, we pick a variable, which is L, and basically say that we can decide anything as long as L is undefined in M. And so for the deduction, which in DPLL is called unit propagation, we say that if a formula contains a clause such that the current assignment contradicts all of the variables in the clause except a single literal, then we can append the literal to the current assignment, which is basically a deduction, because as you've shown previously, if all the literals in a clause are assigned to false, and then the last one must be true in order for the clause to finally evaluate to true. And as such, we are sure that we can make a deduction that that literal must be true. And yeah, and there's also a transition for backtracking, but this is not particularly important. So, so now we also want to formulate the chain of thought process as a state transition system. And the chain of thought process is basically you have a prompt, which is an initial sequence of tokens, and you run the model. At each iteration, you run the model on the current prompt, generate a token, append it to the prompt, and do this again, 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 until the generated token is one of the stop tokens. In our case, it's the set containing set and unset, and just when it encounters stop token, it just returns the entire string containing the up until the final stop token. And we can also model the chain of thought as a state transition system where the states are just V star, which means all the strings containing all the strings consisting of tokens in the vocabulary, as well as the transitions are simply strings, transitions to string followed by another token, where the final token is the result of running the model on the string. And now, how do we prove equivalent relationship between? How do we prove an equivalence relationship between our chain of thought and the state transition system? So this results in the concept of refinement between two transition systems. So basically, we say that a transition system A refines transition system B. We say that a transition system A refines a transition system B if there exists a mapping from the states of A to states of B, which may be neither injective nor surjective, but it must have the property that it maps the start state of A to the start state of B, and for any state of B that can be mapped to by the relationship, then if it has a transition to another state, then there must be a corresponding transition from the source A state, such that after several transitions, according to the transition rules of A, it results in SA/ state, which is after several transitions from the SA state, such that SA/ state maps to the SB/ state, which the original SB state goes to after one transition. So to explain this more visually, the reason that we want to allows several steps of the transition of A to catch up with the transition of B is that, so the refinement mapping for our chain of thought is that you parse this into the F part of the state of the abstract DPLL, and you parse the current prefix into the M part of the abstract DPLL state. And you'll find that when doing, for example, when doing the decision operation, you would first have assume and then have to, and which correspond to two transitions of the chain of thought transition system. But when you consider the abstract DPLL system, it actually only takes one step to make the decision. So this means that it actually takes two steps for the chain of thought to catch up with a single transition of the state transition system of abstract DPLL. So the goal now is to prove that the chain of thought transition system corresponding to our theoretical construction transformer model refines abstract DPLL. And from this we can, and as long as we can show that the chain of thought refines abstract DPLL, and the final state of abstract DPLL correspond to a chain of thought ending with set or nset, then we basically have shown that our chain of thought procedure decides 3 set, because in the paper that proposed abstract DPL, they already have a few theorems showing that the abstract DPL is a correct SAT-solving state transition procedure. Okay, are there any questions regarding this part? Okay. Okay. Now the question is, how do we show that the internal mechanisms of our transformer theoretical construction actually performs SAT-solving? So the idea is that we first encode clauses into vectors. So why is this the case? So basically, for deep learning models and transformers, or any deep learning model in general, all the operations are represented as vector operations. So in order to implement anything as a deep learning model or a transformer model, we need to formalize the operations performed by our desired reasoning system as vector operations. And the idea here is that we formulate both clauses and partial assignments as binary vectors, such that their dot products are very informative. So how we do this is that for a clause, it contains at most 3 literals, right? And for each we have a binary vector where each dimension corresponds to a possible literal, which is a 2p dimensional vector where p is the number of variables, a 2p dimensional vector that contains not x1 to not xp, as well as contains x1 to xp as well as not x1 to not xp. And for each literal, we just set the corresponding position to 1. So basically, because it contains 3 literals x1, x2, and x4, we set the positions corresponding to not x1, not x2, and not x4 to 1. And similarly, for the partial assignment, we just use the symbol conversion of if x4 is assigned to false, it corresponds to literal not x4. x1 is equal to true, it corresponds to literal x1. And x2 is equal to true, then it corresponds to the literal x2. Then we convert it into a vector that uses basically the same encoding scheme as a clause, but for the partial assignment. Now, why do we do this? So recall that in the transformer model, a self-attention layer uses the dot product qi times kj to compute the attention weight between the position I and position j, and essentially we need to make the dot products between qi and kj informative of the SAT-solving procedure that we are trying to do. And the idea is that we would set the binary vector that corresponds to the partial assignment as the query vector, and the binary vector that encodes each clause as the key vector. And then their dot product will represent how many literals in the clause is satisfied by the current partial assignment. Because during the dot product, you basically multiply the positions corresponding to x1 together, or multiply the positions corresponding to x2 together and sum them up, right? And essentially, here we can see that the only variable that is the only literal that is satisfied by the current partial assignment is not x4, because x4 is assigned to false here, and correspondingly, this not x4 position is set to 1 from this clause, and the not x4 position of this partial assignment is also set to 1. So you can see that if a partial assignment sets a literal in the clause to true, then it basically would result in 1 in the dot product between the query vector and the key vector, which is the dot product between the binary encoding of the partial assignment and the binary encoding of the clause. And if we dot product them together, we get the number of satisfied literals of the clause according to the partial assignment. And now why do we do this? So recall again that in the transformer model, a query vector attends to every previous key vector. And if we simultaneously encode all the binary vector of the previous clauses as the key vector and compute the dot product between the partial assignment, which is the query vector, and the key vectors corresponding to the binary encoding of the clauses, then we can simultaneously compute all the number of satisfied literals in every clause. And the formula is satisfied if and only if all the clauses are satisfied, which means that all the clauses have at least one literal set to true. So we do this by we determine whether the formula is satisfied by current assignment by having a dummy node, which basically says SAT, and having a constant dot product of 0.5. And we encode and we modify or do some linear transformations based on the this dot product, so that the softmax operation selects the smallest dot product of all the dot products between the query and key. And if the formula is not satisfied, then there are definitely some clauses for which the dot product between the current partial assignment and the clause is 0. Then in this case, because this attention operation selects the smallest dot product value, then the dummy node of SAT, which has constant 0.5, will not be selected. But on the other hand, if the formula is already satisfied by the current partial assignment by doing the binary encoding and computing all the dot products as attention weights in parallel, then if all the dot products between the partial assignment and clauses have at least value 1, then the smallest value becomes the SAT dummy node, and we determine whether the formula is satisfied by looking at whether the dummy node set is actually selected. And we can have a similar idea for determining whether there's a conflict between the current assignment and the formula. And this is done by doing some additional linear transformations, which I won't elaborate in detail. But essentially, there exists a transformer layer that can perform checking satisfaction, detecting conflict, and performing unit propagation. And we essentially have all of these attention heads in a single layer of the transformer model. And all of the other models are essentially doing pre-processing and post-processing. Okay. And to determine the final token output, it's based on a series of conditional statements. So essentially, if the formula is satisfied by the current assignment, then we output the SAT token. And how to determine if the formula is satisfied, we just see whether the SAT dummy node is selected in my previous description. And if there's a conflict and there are no assumptions, then we output NSAT. And if there's a conflict and there currently are some assumptions in our currently annotated partial assignment, then we output backtrack because we want to find the previous assumption and reverse it. And this prioritized output can be implemented with a linear transformation. Okay, any questions regarding this part? Okay. Now I'll talk about some experimental results that supports our theoretical conclusions and basically discuss some of its implications. So our theoretical result basically shows that transformers, there exists a transformer that can solve bounded three-set problems, but it doesn't really tell us whether it can learn such solutions. And to investigate whether it can actually learn such solutions and whether it fits our theoretical predictions, we try to do experiments regarding out-of-distribution generalization. And the motivation for this is that in a prior work, which is called the paradox of learning from data, learning to reason from data, and they worked with a much simpler logical reasoning problem, but very similar to three-set, and they show that if you sample the logical reasoning problems differently, even though they are within the same length, and if you use a single transformer, a single path of the transformer without chain of thought to try to output true and false for that logical reasoning problem, then it failed to generalize samples from different distributions, even if they have the same size. And the question that we ask here is, can training with our chain of thought help with this out-of-distribution generalization within the same size? Because our theoretical result demonstrate that for any given size, you have a transformer that can solve all problems of that given size. To do this, we generated 3 different distributions of set formulas. And the most difficult one is what we call the marginal 3-set instances, where it's generated from pairs of 3-set instances, one of them being set and one of them being unset, but they differ by only a single token. So it is very hard to use any statistical feature of the formulas of these of the set versus unset instances to gain any information, because out of the 160 or so tokens, only one of them differ from each other. So their statistical properties are almost exactly the same. And we also generate 2 different distributions that does not demonstrate this property. And the question is whether models trained on the 2 other the two other distributions can generalize to solve the hardest 3-set problems and vice versa. And we just trained llama, miniaturized llama models based on our chain of thought that was described here. And we demonstrate that, yes, the large language model, the transformer models trained with our chain of thought can demonstrate sort of intra-length out of distribution generalization, in that they basically achieve 1 minus epsilon accuracy, even if they are trained on differently sampled data set instances than the test set. So basically, these matrices represent the horizontal rows are the data set that we're trained on, and the columns represent the test set, the test set instances that they were tested on. And you can see that for both number of variable ranges, 6 to 10, 11 to 15, they basically demonstrate almost perfect out of distribution generalization. But we also demonstrate that as long as you go up beyond the number of variables that they've seen during training, then its accuracy falls drastically, which basically fits our theoretical prediction that you need different models to account for different need different models to account for different lengths of the formulas. Okay, and finally, I'm going to discuss a little about why such limitations in length generalization happen and potential solutions to it. So the reason that a different theoretical construction is required for different implements is that we would actually want to each attention layer to only gain information or attend to the desired positions. Because if you think about it, when you're implementing a discrete algorithm, you only want to read from one memory location at a time instead of a linear combination of the content of all memory locations. But that is not the case in vanilla transformers, because the vanilla transformers with the self-attention operation uses softmax, but that doesn't allow exactly zero attention. And to address this, for every implements, we need to scale the attention weights differently, so that the attention noise, basically the attention strings to unwanted positions, is bounded beyond a very small threshold. And because for a smaller implements, the scaling factor is smaller than those required for longer implements, then a transformer trained on a smaller implements may not learn such a scaling factor that can be generalized to those required for longer implements. So there are a few potential solutions to this problem. And the first one is basically concurrent work of ours, but from another group, that basically proposes the architecture that uses a separate, that basically performs two Q times K dot products and try to cancel the attention noise. Okay.
Summarize your talk with 1 minute.
Okay, yes. And we also have two other suggestions, which is one to use directly use RELU activation instead of softmax to allow zero attention, and also construct a transformer model that performs the internal scaling so that it scales the attention weight by the current length. And that's the end of my talk. Thank you very much.
Yeah. Any questions? Yeah. I have one question. So I'm not sure if I understand the talk. I fully understand the talk. So I think the first part you're more talking about the expressiveness of the transformer.
Yes.
It can represent it. And but I didn't quite get the point that how to train such a transformer efficiently. I think you just mentioned you want to use chain of thoughts, but I didn't quite understand like what is your training data? You just constructed such chain of thought and use it as training data,
Yes.
and then just doing optimization over the training data, and then you can obtain the model.
Yes.
And did you justify that the model actually follows the chain of thoughts? Like how could you verify it's actually calculating, solving the
Oh, yes. So you can have a verification procedure, and basically what I didn't show here is that and you have a slightly lower accuracy, obviously, for if you require each reasoning steps to strictly follow the abstract DPL algorithm, but basically it's still on the range of 1 minus epsilon.
Okay. Yeah, and a high level question. I didn't really understand like so when you say the transformer can reasoning can do reasoning, you just mean that in the end you can output transformer that follow chain of thoughts. That is your definition of reasoning?
So in a 3-step problem, we want to follow a decision procedure that does step-by-step reasoning. And by reasoning, we mean that a procedure that will deduce facts from existing ones. And then we combine that with trial and error, which basically assumes variables and assign them a value. And essentially, what we showed is that there exists a transformer that can strictly follow this procedure and eventually obtain SAT or NSAT.
Thank you. Yeah,
Thank you very much.
Okay, so let's start.